So yeah, all right. I'm gonna slowly start and hope that the rest of the attendees join us. So yeah, greetings everyone. It's my pleasure to invite you all to my master thesis colloquium on the topic noise robust speech recognition for search and rescue domain. To give you a brief idea about this work, we basically try to do speech recognition, simply as you know, but in a very specific kind of domain that is hostile and that is filled with noisy, and contaminated with noise-filled surrounding. And this kind of the kind of noises that we deal with are very common in search and rescue mission. Like when a search and rescue mission happens, you have crowd noise, you have chopper noise, you have emergency vehicle siren, these kinds of noises. So this is the goal of our work. So this is the layout of the presentation. We will begin with introduction, then we'll describe the motivation behind the project and the contribution that we make through this work. We'll go a bit deep into the literature survey and learn about the work that has been done in this area in the past few decades. And then we will come to the boring part where we'll discuss the technical background. We'll go over the architectures, the model, and everything. Then we'll discuss the dataset that we have used and also the dataset that we propose in our work. And then we'll discuss the training strategies and the results that we achieve and how we analyze them. We end this presentation with a few concluding remarks and how we can improve over this on this work by suggesting some ideas of improvisations. This presentation is going to last about 35 minutes, and I will take a few more minutes, around 2 to 3 minutes, to show you a live working demo of this entire thesis of entire work. So let's jump right into introduction. So technology, as we all know, we have come a long way, especially in the field of communication. We have, from typing keystrokes to touch screens, and now we are doing speech recognition. And this basically enables us to translate these spoken words or the utterances into text. However, technology as easy as it seems, it's never that case. So we face several challenges that we have. So we have low resource languages, languages where we have very limited data to train for. We have issues with accent or dialect differences. We have domain mismatch. Think of an example where you train a speech recognizer on for example, European Parliament data and test it on some university mathematics lecture, so you will have miserable performance. We also have issues with noisy surrounding, which is our main focus. It fails terribly. Try using Google's speech recognition or Apple's even when you have crowd noise or in a cafeteria or in a market. So there will be some deterioration in the performance. And my thesis focuses on developing a speech recognition system that is robust to noise, that is most common during search and rescue mission, especially for German language. So the search and rescue domain is like very critical, where the goal is to provide quick and accurate communication to save life and mitigate the damage of property. It involves, locating victims on isolated spots, rescuing and providing medical assistance to people or to individuals who are in distress. And the kind of noises that we deal in this work is like the search and rescue noises, basically the chopper noise, we have engine noise, emergency vehicle siren noise, we have static radio noise that happens when these rescue members speak over their radio phone. Then you have heavy breathing noises because all these rescue workers have masks attached to their put on their mouth, and they communicate with other rescue members. Now let's discuss the motivation behind this idea and the contribution that we make. So this project is dedicated to the ADRZ project, and in disaster situation where efficient communication is critical component into saving lives and mitigating the damage. And we all know that emergencies like residential fire, or you have a building collapse, or for example, you have nuclear accidents, and these kind of situations often exceed the human capacity. I mean, this is where we need these voice-enabled robots to help assess the accident site or provide efficient communication among the rescuers. And but again, I mean, for these robots to go into the such accident sites, they have to be situationally aware of such events. So what we do is power these robots with SLU, like spoken language understanding, to enhance communication in disaster scenario, and also power them with a situational awareness knowledge. Let's take a closer look into the speech processing component. So here we have the audio, and then we do the transcription using a noise-robust speech recognition that we build in our work. Then an NLU component is integrated that extracts meaning from this text, and it maintains the state of the dialogue. And further, there's a post-processing component that again collects these information and tries to or re-ranks the hypothesis if that's needed. So through this work, we address basically two challenges. So first, we solve the problem of lack of search and rescue speech data by recording our own data and annotating them with the help of language experts. And then we release them to the public. We call this dataset the rescue speech dataset. Next, we also try or attempt to propose our own systems that is robust to SAR noises that we discussed earlier. For this, we propose multiple training strategy, like we do multi-condition training, then we train speech enhancement and integrate with ASR to allow the noisy utterances to clean and then do the transcription. We believe that with the release of our rescue speech dataset for German language, can be used to establish a common benchmark among researchers for further research in this field, because we were like literally, I believe, first one to release such a data. I mean, especially for German language. Even for English language, I couldn't find any data. I mean, even if there is data, I mean, they haven't released it publicly. So it was quite challenging. Now let's go into literature survey for ASR and speech enhancement and discuss the SpeechBrain toolkit that we have used in our work. So ASR, the first ever ASR known was the Audrey, dated back to 1952, launched by IBM and it was designed to identify numbers. Further, in the 1980s, saw a significant progress with speech recognition. Speech recognition with these HMM-based model and the Baum-Welch algorithm. Artificial neural networks gained popularity in the 1990s, where the networks were being used to discriminate among very limited vocabulary of words. And in the 20s, HMM-based ASR gained popularity with the use of GMM, where each speech unit, for example, phoneme, was represented as a GMM distribution in an HMM state. And then post-2012 saw the rise of deep neural networks inspired. So HMM and deep neural networks were used in combination. And then came the era of end-to-end model, where you basically replace all components of a non-modularized ASR system with a single DNN-based model. So instead of having a multiple components or multiple objective functions to train your pronunciation model, your acoustic model or language model, what you do is that you have a single objective function you just have a single objective function and you just train that to get your transcriptions. So there are several end-to-end approaches that we look into our work. That is the CTC and the attention-based encoder-decoder-based model and the RNN transducer. And these are the few one of the best or popular training architecture that and we have used all of them to we also pretend them, and then we make comparison between each of these models. Now let's take a closer look into how speech enhancement has evolved over the years, over the past few decades. One of the traditional methods for speech enhancement is spectral subtraction, that estimates the noise power spectrum and subtracts it from the noisy speech spectrum. I mean, once the subtraction is done, you get the clean signal. Wiener filtering is another method that minimizes the mean squared error between the reconstructed and the original spectra. Around in the similar time, there was this another technique called as Kalman filtering that was proposed for speech enhancement that basically uses the speech production model. In the 20s, we had plenty of Bayesian approaches-based model, for example, MMSE, STSA-based model. Post 2012, again, similar to ASR, there was quite significant work done in speech enhancement using DNN, where researchers aim to handle, unseen noisy condition and low SNR level. So when the SNR level is low, you have more intensity of noise in your speech signal. So recently proposed model, for example, this mimic loss, Metrogan, and SEPformer, they use or leverage the DNN. For example, this Metrogan architecture uses generative adversarial networks to optimize generators and discriminators to achieve multiple evaluation metrics. And all these rest of the models, they use unique loss functions, a perceptual acoustic model, self-attention transformer-based networks to further improve the speech intelligibility and speech separation. So our work makes an extensive use of the SpeechBrain toolkit. So let's talk a bit about this. So SpeechBrain, as who use, we all know that it's an open source conversational AI toolkit that aims to replicate the functionality of human brain, hence the name SpeechBrain. It's like super flexible, modular, efficient, well documented. You have plenty features. You have ready-made recipes for ASR, speaker ID, language detection, speech enhancement, and dialogue processing tasks, and so on. It's easily compatible with lot of data actually that is available online, and that is formatted with JSON and CSV. So if you need to train any model, you can use the ready-made recipe and format your data in this in these types of file and just train simply by passing a SpeechBrain formatted hyperparameter file and train your model. Now let's come to a bit of a boring part where we discuss the our end-to-end models for ASR and speech enhancement. So first, let's take a closer look for the ASR, where we have two end-to-end models, the CTC and the attention-based encoder-decoder models. So the CTC is designed to align the input acoustic frames with with output labels. So its job is to basically tell what must have been spoken over in a particular speech or acoustic frame. And it does this by modeling the probability distribution at each of these time steps. So you see here T1, T2. I mean, it's not written, but each of these are consecutive time steps, and it computes probability distribution. So let's take a closer look into this picture and understand how this happens. So once the training begins, these input sequences are fed into an RNN network, after which it computes the probability of each output. So for example, at this time step, it computes what is the probability that here H was spoken, or what is the probability that here E was spoken, L was spoken, and so on and so forth. So it computes these probabilities for each of these time steps. So in the end, you have a matrix of probability. And here you see this epsilon symbol. This is basically a blank a symbol for blank token that is introduced to solve the problem with unequal sequence length, because you know your speech signal is quite long, but your transcription is like really small. So the blank token basically handles that kind of unequal sequence length. Now, once you have the matrix of probability, what CTC does is compute the probability over all possible valid alignments and sums them over. So, for example, here it took the maximum, it took H as a valid alignment for this for this time step. It took E as the most probable spoken letter at this time step, and it forms similar valid alignments and marginalizes. Basically, it sums the probability over all possible alignments, and what you get in the finally is your final. In the end, you get your final distribution. So once the network is trained using a loss function, its job is to determine the most probable output sequence for a test input. And it does this by using a beam search algorithm. Now, the second model that we have used is a simple attention-based encoder-decoder model, wherein it uses attention mechanism to focus on different paths of the input speech. So here the encoder can be like any bidirectional LSTM that encodes acoustic feature into high-level vector representation. Next, attention is applied to each part of the input sequence to determine which part of the input sequence is relevant to the current decoding step. And it does this by computing weighted sum of the encoder's output and previous decoder's output. In the next step, the decoder takes the context vector and the previously computed output to estimate the probability of the current label. And it further passes through a softmax to get you the probability of the current label. Next, we take a look into the two models that we have used, CRDNN and wave-to-vec. So CRDNN is like one of the classic methods for speech recognition. It's like a simple combination of convolutional neural network, recurrent neural network, and dense neural network, followed by a linear and a softmax layer to get you the probability. So it takes in input 40 male filter bank coefficients, and the CNN layer here performs spectral modeling. So you have like two CNN blocks to do the spectral modeling. Next, the RNN block here performs time series analysis, and the DNN layer captures the long-range dependencies between the transcriptions and the input, your input speech features. And the fully connected layer and the softmax gives us the probability of the predicted label. And for this, for the decoding here, what we do is we use beam search and an RNN-based language model on top of the decoding probabilities. Here, it predicts unique terms as the fundamental recognition units. While wave to vec is a bit different, it's like a self-supervised model for learning speech, actually high-level speech representation using unlabeled data. And it acts very similar to BERT. And the unique thing is that it's trained on large amount of unlabeled and unannotated audio data. And later, once the training is done, we fine tune on labeled data for our downstream tasks. So let's take a closer look into the architecture here. So once you have the raw audio form, raw waveform, you use a CNN feature encoder to produce intermediate representations. Then we have a transformer network here that uses self-attention and relative positional embedding to capture the long-range dependencies between your acoustic speech, your acoustic units. And here the acoustic units are your the frames, the input speech frames, and they can be like really small window, for example, 25 milliseconds or so. Lastly, we have this green ones, the quantization that is used to generate discriminative speech embeddings. And to put it simply, the entire pre-training, this is the entire pre-training, it is done to, what it does is that it basically covers certain portions of the speech representation, and the model is trained in a way to predict what has been masked or what has been covered, and also what has been spoken on that very masked portion of speech. Now we take a closer look into our speech enhancement model here. So the speech enhancement model is our subformer architecture. It's a multi-head attention transformer-based network, very similar to what you see in the paper, attention is all you need. And it was initially proposed for speech separation. It uses a fully learnable masking network composed of an encoder and a decoder here. So the encoder and decoder here are basically convolutional layers, and what we do is we learn a deep masking network here, and the model is trained in a supervised fashion using scale invariant signal to noise ratio loss. So let's see the masking architecture in a bit more detail. So here it takes an input, the encoder output, into a normalization and a linear layer, followed by you have chunking with overlapping, and then you have the subformer, which is the main attraction here. So the subformer is made up of three blocks: the intra-transformer, the permute block, and the inter-transformer block. So what intra-transformer block does is that it captures short-term dependencies, and the permute block rearranges the output dimension, while your inter-transformer block models the long-range dependencies. And you have several of these blocks repeated subsequently. In the end, you have here the decoder that takes in the masked representation and the encoder output, and then it performs some element-wise multiplication. In the end, it spits out two sequences or multiple sequences depending upon how many. I mean, for example, if you had an audio mixture of three people, it spits out three sequences. But for our case, we have two outputs, because our audio is mixed with a noisy clean audio and a noisy audio. So it spits out a estimated noisy source and the enhanced speech signal here. Yeah. Now, let's talk about the evaluation metrics. We primarily, for speech recognition, we use word error rate. That is a simple sum of number of substitutions, insertion, and deletion averaged over total number of words in your reference text. But for speech enhancement, we have several metrics, and they can be broadly categorized into intrusive and non-intrusive metrics. So intrusive metrics, it means that they compare a reference clean speech signal and enhanced speech signal, while the non-intrusive metric, they do not need any reference signal to give their score or to generate their score. So the improvement in scale invariant ratio, or improvement in scale invariant signal to distortion ratio, are based on energy comparison, but SDR is like a bit better because it takes into account scaling in the signal. And here higher scores here higher scores indicate you have better quality of enhancement being done. We also have two metrics, PSQ and STOI scores measured on a scale of minus 0.5 to 4.5 and 0 to 1. And here higher scores indicate better intelligibility. Then we have the non-intrusive metric like a DNS MOS, which is the deep noise suppression mean opinion score. It was basically launched or basically introduced as a part of the deep noise suppression challenge that takes place annually every year. So basically, why it does not need any reference signal is because it uses, it is basically, this metric is like a trained model, a convolutional neural network based model trained on human ratings, and therefore it does not need any reference signal. And each of these metrics, speech quality or background speech quality, overall quality, are measured on a scale of 1 to 5, where 5 being the best quality enhanced speech signal. Now let's take a closer look into the data set. Okay, so I'll try to wrap it up quickly. Now we are running out of time. So we use, in our first stage of pre-training, we use a common voice dataset to train our speech recognizer, and we use the DNS4, which is the Deep Noise Suppression Challenge 2022, the fourth version of the challenge, to train our speech enhancement, that is a SEP former module, So the common voice is used to pre-train these models, the CRENN, Wave2Vec, and WaveLM. It basically amounts to roughly 1,200 hours of dataset, labeled dataset. And in the DNS dataset, we synthesize around 1,300 hours of clean and noisy pairs, where we basically mix 150 types of noises varying multiple decibels from -5 to 15. And we also add reverberation, like we basically 30% of the entire training data is convolved with is basically reverberated to replicate real training. Real training, real life application. Yeah. Next, we introduce our rescue speech dataset, which is achievement from our work. So we the goal of this rescue speech dataset is to fine-tune our ASR and the enhancement model. So we have two versions of the dataset. We have the clean version and the noisy version. So clean version is the one that was initially recorded as a part of several simulated search and rescue exercises, while the noisy version is artificially synthesized from the clean version by adding these kinds of noises. Emergency vehicle, breathing, engine, chopper, static radio noise. And the source of these noises is the audio dataset. Next, we describe the experimental setup. So in the first stage, that is the pre-training stage, we do ASR training and we do speech enhancement training. In the ASR training, we saw CRDNN sequence to sequence with beam search accompanied with a language model. Wave-to-vec CTC, we simply used a greedy decoder because these models do not need any language model because they are based on CTC. I mean, it's not that we cannot use. If we use language model, the performance will be further improved. But for this, at this time, we haven't used any language model here. WaveLM also CTC with a greedy decoder and the Whisper by OpenAI, the recent or the current state-of-the-art ASR model. It needs no pre-training. Whisper, I remember it has been trained on like 680,000 of multilingual multitask data, comprising of approximately 96 languages. So you basically do not need pre-training. And for the speech enhancement, we do the pre-training of Subformer on 1,300 hours of our DNS4 dataset. Next, we'll discuss a few training strategies. So what we discussed here was basically ASR and speech enhancement training, but we need to do something extra for our specific domain. And this is how we introduce multiple training strategies. So the first basic strategy is the multi-condition training strategy, where we basically supplement our clean audio with equal proportion of noisy audio, and we train the ASR model. So we believe that this way the ASR model will learn to understand the noises in the data without having any speech enhancement model before it. And the results that we get from here will be our baseline results for our rescue speech test set. The next strategy for noise robust speech recognition is the independent training approach, where we have the pre-trained subformer model and we fine-tune on the rescue speech dataset. So we have the fine-tuned model here and we have the fine-tuned ASR model. And we basically combine both of these and do the speech recognition. So basically the enhancement model gives us the enhanced waves, and then we use ASR to get transcription and compute a variable rate. The important thing here to note is that the enhancement model is frozen. It means we do not let its gradient update or let its weight update during the training process. In the last strategy of joint training, we basically unfreeze the enhancement model and allow the loss to share and gradients to update. So basically, what we believe it does is the ASR model dictates the enhancement model how it should clean the speech that would result in an optimum word error rate. Okay, so now I think we can jump into the results and the discussion. We make some analysis. So our first stage, if you remember, we did the pre-training stage where we pre-trained the ASR model, and we pre-trained a subformer speech enhancement model. So in the pre-training stage, we used the model trained earlier and simply tested on the common voice here test set. So here, if you see the CRDNN, the classical model CRDNN with accompanied with language model, the word rate is 7.92, and it's like very competitive or very close to what we have with WaveLM and Wave2Vec2, even though they have been already pre-trained on 1,000 hours of unlabeled data. So here, the performance is like very competitive because CRDNN leverages a language model during decoding that captures, structural patterns in your data and corrects error made by the acoustic modeling. While if you see our subformer model performed below the baseline model, which is NSNet2, this basically failed to improve the perceived quality of noisy speech signal compared to the baseline model here. So this is our first attempt to noise robust speech recognition, and we see the results here. So here we created a simple pipeline consisting just of an ASR, and like we don't have any speech enhancement system here. So in the pre-training stage, we use the models that we train here. We use these models that we train here and simply test it against the rescue speech clean inputs and noisy inputs. In the clean training, we only fine-tune these models on the clean version of clean version of a rescue speech dataset. While in the multi-condition training, we supplement our clean dataset with equal proportion of noisy dataset, and we let the ASR model, these ASR model fine-tune themselves. So the word rate that you see here, this will be our baseline, and we compare this score with our next attempt to noisy speech recognition, which is the joint model training and the independent model training, the model combination 1, and the joint training, which is the model combination 2. So we clearly, so here we clearly see an improvement in the speech enhancement metrics across all speech enhancement metrics, because here we share the loss, and here we basically do not share the loss. Then we compare the final speech recognition output for all the models that we have here, and conclude that the independent training approach, the model combination 1, is indeed better than joint training. We basically conclude that the enhanced output from the frozen enhancement model is better compared to the unfrozen one. We basically mean to say that this model, having the enhancement model unfrozen basically emits enhanced speech, but that is not suitable for the ASR. So this architecture, this training strategy is the best performing, with the ASR model being whisper and the enhancement model frozen being SEP former. So the best reward rate that we have is 30%. Now we do some visual analysis. On the left, we show a log power spectrogram of clean, noisy, and SEP former enhanced utterance for 2 noise types, emergency vehicle siren and chopper. And we inspect how here the noise was eliminated upon enhancement, and you can see these bright patches being removed or eliminated. To the right, you can see PESQ scores versus SNR and SISNR or SDR versus SNR. And we observe that the improvement in the SNR and SDR were greater for utterances with -5 decibel, indicating, more significant enhancement than for higher SNR. Basically, when you have -5, it means you have more noisy content in your speech signal. Hence, the improvement is quite big. And this type of pattern, this pattern is consistent across all noise types. For PESQ scores that you see here, when the model is too noisy, the enhancement model works, but it is not significantly good. So here you have very less PESQ scores. But when there's very little intensity of noise being added to your signal, you have very high PESQ scores. Now it's time we make some concluding remarks. So we introduced our rescue speech dataset. We addressed the lack of, via our dataset, we addressed the issue of lack of speech dataset in SAR domain. We addressed the issues with search and rescue type of noises. And we proposed multiple training strategies. We saw a cutting edge self-supervised model, and despite training or fine-tuning each of them. Even Whisper, our best word rate was approximately 30%, highlighting like we are really far from having an acceptable performance. There are lots of future work, actually, lots of room of improvements in this work. So we should like take into account the channel characteristics during training, like factors like noise, reverberation, interference, etc., that affect the noise quality as the audio travels from from a speaker to a microphone. Other improvements include extending this data set to other languages and using data augmentation techniques to generate more SAR data, because the SAR data that we have right now is like barricaded with privacy restriction and not usable for research. A few improvements include comparison with other speech enhancement model and issues with highly emotional speech. And we have to address also additional noise types that you see in in search and rescue, like you have foot stomping noise, you have structural noise, vibration occurring when you have choppers flying over your house, you have interference types of noises. So all these must be addressed. So this time I show you a working demo of this project, enough of boring talks, and let's see something working in real time. So I'm going to stop the presentation here. I'm going to share screen here. Please object me if you do not hear my audio or the audio from this screen. So let's take a closer look how the clean audio not looks, but how you hear the clean audio, the noisy audio, and the enhanced audio. Here I also put the actual transcript that was annotated, and the predicted transcript by our best ESR model, which was Whisper. So here we have emergency vehicle and siren noise recorded at -5 decibel, which is the highest intensity that we used in our training data.
Abbrechen, wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
Now the noisy audio.
Wenn der Aufwand nicht durchführbar ist, abbrechen, wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
Now let's hear the enhanced audio, and you can also take a look into the predicted transcript.
Wenn der Aufwand nicht durchführbar ist, abbrechen, wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
So you can also see in the log power spectrogram how the noise patches were eliminated upon enhancement. I mean, it's doing its job, but it's still far from being acceptable. Let's try another noise, the engine noise.
Die Drohne meldet 2 Personen im oberen Container des Bürokomplexes kommen. Die Drohne meldet 2 Personen im oberen Container des Bürokomplexes kommen.
The enhanced audio now.
Die Drohne meldet 2 Personen im oberen Container des Bürokomplexes kommen.
Okay, let's take a final example of this breathing noise. It's not.
Das heißt für uns, die Kommunikation mit den Drohnen vor Ort läuft ab sofort dann über euch. Das heißt für uns, die Kommunikation mit den Drohnen vor Ort läuft ab sofort dann über euch.
I'm not sure if it was human panting or a dog panting noise, but it's still heavy breathing.
Das heißt für uns, die Kommunikation mit den Drohnen vor Ort läuft ab sofort dann über euch.
And yeah, that will be the end of the demonstration. Thank you.